Good morning, everybody. Welcome to the discussion meeting on Representation Theory 2020. Um, so before we begin, I just want to tell you about the format of the lectures. The lectures are going to be 1 hour long, and we'll have a question break after 30 minutes. You can type in any questions that you have into the chat box, and I will interrupt the speaker at that moment if needed, or ask him the questions during the question break. Otherwise, I'd request everybody to keep their microphones muted. And at the end of the lecture, again, we'll have a longer discussion session at 10:30. So with that, let me introduce the first speaker. It's really a great pleasure to have Professor Arun of the University of Melbourne. He's going to give a series of lectures on Macdonald polynomials, and the first of these is examples of Macdonald polynomials. Arun, please take over.
Thank you. Thank you. Well, thank you very much for having me for this workshop. It's always a great pleasure to be able to tell the stories which we are thinking about. And I'm very much entranced by these affine combinatorial, really moving to the affine Lie algebra in several aspects. And so I've divided the talks into 3 parts. One is, the first one is Macdonald polynomials. And the second one is on level 0 representations of the affine Lie algebra, or the affine quantum group. And the third one will be a bit about transfer matrices and R matrices and those kind of things. All of the talks I'm going to focus on GLN. In fact, I made the series of lectures so that for me it was an excuse to do some examples, which I should have done many years ago, and I'm trying to work them out clearly so that everybody could see. But I thought that was also very nice for people who are learning the subject to see it come through in the examples. So I'm going to try to build a few examples. Okay, so let's start with the affine Vial group. So I put the presentations of the affine Vial group here on this slide, but in fact, I want to not really focus on the presentation at first. So this is the affine Vial group will be W, and I will look at the GLN for these examples. And in this case, it acts on just the n-dimensional lattice, z to the n, so integer lattice. And the action, so the generators of the affine Vial group, you should think of them as transformations that are acting on the lattice. So I have first these SIs, S1 up to Sn minus 1, and then one additional element, which we call pi. So this is special to GLN that you have this pi. If you were working in other types, you would have to maybe use an S0 instead. But in GLN, we use this pi, and it's very convenient, very useful. So the action is given as follows. I'm going to take SI and act on a sequence mu1 up to mu n. So let's put I plus 2 there as well. Mu I plus 2 up to mu n. So this is just a sequence of integers. And SI just transposes the ith and the I plus first spot. So the first I minus 1 stay the same. And then I switch the I plus 1 and the I, and continue, the rest of them stay the same. So the only thing which had happened here is that these two have gotten switched. So this is SI. So those SIs, they of course generate a symmetric group, symmetric group Sn, and pi, when it acts on a sequence, mu1 up to mu n, it takes the last element of the sequence puts it at the front, moves it around to the front and adds 1, and then puts the remaining elements of the sequence following. So it cycles around like this, but each time you cycle, you add 1. And so this gives us an action of W on this lattice. And Sn is the subgroup generated by just the group. Okay, so now I want to let's suppose that we have fixed some element of the lattice, so sequence of integers. Associate to this sequence of integers 2 things. I'm going to associate a v mu and a u mu. So v mu is going to be an ordinary permutation, and it should be the minimal length such that I want v mu to act on mu and put it in increasing order. So you can imagine the elements of mu, and I have to make some rearrangement in order to get them to be increasing. And whatever this permutation is, whatever the shortest way to get it to be increasing, that's the v mu. And the u mu is actually an element of the affine Vial group, so I will have to use pi to make u mu. And it should be minimal length, such that, so I want to take u mu and act on 0. That's a sequence of integers, so I want to start at 0 and arrive at mu. So I have to use some sequence of these operators to start at 0 and to arrive at mu. We will do an example. Let's do an example of these 2 things. So my example is going to be just the case n equal 3. And let's take mu to be 0, 1, 2. Well, this is very easy. V mu for this case is the identity, because mu is already increasing 0, 1, 2. So I don't have to do anything. That's the shortest one. But if I want to, let's figure out what should u mu be. So what is now u mu? And so we'll start, so I'm going to do it backwards. I'm going to reverse it. I'm going to start with mu, I'm going to start with a mu and go back to 0. And in this way, I will compute u mu. So first thing I can do is switch the first 2 positions. So S1 switches the 0 and the 1. They are in positions 1 and 2. And then if I apply pi inverse, I will remember what did pi do is the action is not here. Let's take a picture so that you can remember these operators. There. Okay, so now we have these operators. So pi is this operator that moves the last one to the first place and adds 1. So pi inverse will take the first position and put it at the end and subtract 1, and then move the others to the left. So 0 to 0. So this is pi inverse. Now if I do S1, I'll move the 2 to the beginning, and I can do pi inverse again, and it takes the 2, moves it to the last place and subtracts 1, and then moves the other 2 zeros. So you see, each time the value of the integers is going down by this process. I'm making a shortest path. So now I'll do S2, which moves the one that switches the third and the second spot. And then I do S1, which puts the one in the first spot. And then we'll apply pi inverse again, and we get to 0. So the effect of this computation is that it tells us that u mu is equal to S1 pi, S1 pi, S2, S1 pi. Right, that's exactly the thing, which when you act on 0, it will take you back to 0, 1, 2. And
you haven't really explained why it's the shortest path, right? We need some measure of the length.
You have to convince yourself that I am doing it in a sensible way. So in fact, I agree that there's some argument to be made that I always take if there's a 0 at the initial place, then I move it, the non-zero element to the left, to the first position. And then I use the pi to rotate it around. So in this way, I have a fixed sequence, which is producing me this minimal length element. But in fact, this is an old algorithm that I'll call the box greedy algorithm. And if you know the world of Macdonald polynomials or Jack polynomials, this was used early in the theory by Knoop and Sahi, and then later by Hagle and Taimendlor. But I agree with you that probably you should write a proof that I haven't lied, that we are directly down to 0 in the shortest way. Okay, so for the combinatorics part, it's very, especially in GLN, there's a lot of literature about Macdonald polynomials, which uses boxes. So we're going to write this word in terms of the boxes. Maybe I should make it a bit larger boxes. So I put 0 boxes in the first row. In general, I put mu I boxes in row I. And then I'll put 1 box in the second row, because this is the 0, 1, 2. And I'll put 2 boxes in the third row. So I could label the rows. The rows are 1, 2, and 3. And in the boxes, I'm now going to put these factors, which we have obtained. So this is a way of using the reduced word for this element of the affine Vial group to think of it, to express it in a box by box form. And if you work with the GLN Macdonald polynomials, this in fact will be crucial to our combinatorial formulas. So hopefully that explains how we make this u mu. V mu and u mu are two affine permutations that we will use to build the Macdonald polynomial.
Yeah, so there's a question from Pooja Singla. She wants to know if V mu and U mu are uniquely determined.
So the elements themselves, they are uniquely determined, but there could be several reduced words. So there could be several paths of the same length, which take you from mu to 0. So there could be, the reduced word is not unique, but the element itself is unique. You can write it as a minimal length representative in a certain coset of the finite Vial group. Okay, good. So the next thing that we want to construct is the Daha. So the Daha is really the crucial object for building Macdonald polynomials. This was the creation of Cherednik for really giving a foundation to the theory, an algebraic way of working with it. So I need to fix double affine Hecke algebra, I should say. This is a double affine Hecke algebra. Okay, so I fix t to the half is a parameter and q is a parameter. We can just take them to be non-zero complex numbers for them, but they will appear as parameters in the algebra. Now the generators of my Daha are, well, I'll have T1 up to Tn minus 1, and then I'll have a G and a G check. You see, this is already somehow trying to be a Daha, a double affine thing, because here you have one affine, and here you have another affine. So this is why it's, so the G is somehow taking the place of pi, and the TIs, the T1 up to Tn minus 1, it should be Tn minus 1, sorry, are taking the place of S1 up to Sn. So when I go from the Vial group to the Hecke algebra, the S1 up to Sn minus 1 are changing to T, and the pi is doubling and giving me both a G and a G check. Okay, so I will write the relations down here. So in fact, I wrote down 3 presentations, but of course, the first time you see this, it's somehow impossible to absorb all of these relations into your head and to work with them. So I'm not expecting that we can really think very thoroughly about these relations at this point. So there's one way of writing it. Then just to make it more confusing, there's another way of writing it. And then to make it more confusing, there's a third way of writing it. So there are three very common presentations of this double affine Hecke algebra. But let's just...
But yeah, there's just one more question from Irfan Habib. He wants to know if there's any relation between G and G check, or are they just unrelated symbols?
They are related. So in this bottom part here, you see that T1 G check G is equal to G check Tn minus 1 inverse. So there is some twisting. They don't operate completely independently. Yeah. For the moment, let's learn how to work with this algebra, ignoring the relations at the beginning. So let's define, I'm going to define y1 up to yn and x1 up to xn. These will be elements of the Daha. And we'll define them as follows. So y1 is g Tn minus 1 down to T2 T1. And x1 is similar except with G check. G check, and I use the normalization that has inverses. Okay. So I have, this is y1. And then if I want to get yj plus 1, I take yj and I conjugate it with, well, just tj. So that's the tj inverse on both sides. So it's not a conjugate. I really smash it with tj inverse on both sides. And if I want to get xj plus 1, I take xj and I smash it with tj on both sides. Okay, so this is a construction of some elements. But then there's quite an amazing proposition, which one has to prove using all the relations, whichever set of relations you decided to start with. And that is that if you look at the x's, they commute among themselves. And if you look at the y's, they commute among themselves. So I have these large abelian subgroups inside of the double affine Hecke algebra. And very often we will think of them as operators. So sometimes the yi's are called, often called Cherednik-Dunkel operators. And they are some sort of generalization of what are called Murphy elements of the symmetric group, of the group algebra, the symmetric group. But that doesn't matter. You don't need to know anything about these operators. But the key word is operators, is that if you have a bunch of commuting operators, so many commuting operators, that reminds you of physical systems. So you would like to try to compute the eigenvalues. Can we find simultaneous eigenvectors? And we use these as integrals for our system, and can we for them? This is somehow just philosophy. You don't have to. This is philosophy. Okay, so I have these wonderful elements, x's and y's, and they commute with each other. So that's the point that we're up to now. And you'll see, maybe we'll copy this proposition so it can live a bit longer.
Yeah, I have just one question about the relations that you've written down. So the generators are only, there's no S0 or S0 check in the generators. So what does it mean when you have them in the relations?
Well, I create S0 by this relation. I use this as a definition. Okay. And then the second one becomes a relation. So it's just a convenient way. I only need these generators G check up to G. And so so I just create the other generators in order to write the relations in a short form.
Yeah. Thanks.
Great. Okay, so these are my elements X and Y. Now, to build Macdonald polynomials, I need one more gadget, and that is intertwiners. So this is intertwiners. So we're going to define tau pi check to be G, and we define tau I check to be, well, in fact, let me define t to the half tau I check is t to the half ti plus 1 minus t divided by 1 minus yi inverse yi plus 1. So if I want to be technically correct, I have to take the field of fractions and the y's and so on, but let's ignore that. Let's just use this as an expression which we will apply using the relations that we already have on these slides over here. Okay, so these are the elements. So this is for I between 1 and n minus 1. Now these are really wonderful elements, these intertwiners, because they have the following phenomenon. So let's let yi plus n be q times yi. This is so that I can talk about yk makes sense for k and z, right? Because each time I am periodic by n, I plus n is the same as multiplying by q. I minus n is the same as multiplying by q inverse. So before I had only 1 up to n, the labels on the y's were 1 up to n, but now I make it periodic by n, but each time you go up in the cycle, you multiply by a factor of q. So this is a trick to write the relations in a nice way. And it really shows the periodicity of, we will see throughout all 3 lectures, there's a lot of periodic phenomena in these affine theory. Okay, so now yi tau pi check is equal to tau pi check yi minus 1. So this is a theorem now that if you move this this yi past this intertwiner, then it just reduces the values of the index by 1. So this is for all integers. And if I take yi and I move it past tau I check, I get yi plus 1. If I take yi plus 1 and move it past tau I check, I get yi. And if I take yj and move it past tau I check, I get yj for j between 1 and n with j not I or I plus 1. So for all the other cases. So now I have some operators which just move past the y's, or the y's will move past the tau's in a very controlled way. So let's keep track of that. Actually, this this doesn't okay. So now let's build the Macdonald polynomials. So the polynomial representation. So this is the representation of Daha. One way to write it down is that it's the induced representation from affine Hecke algebra of the trivial. So you could think about this. This is a trivial representation of the affine Hecke algebra, and H is generated by T1 up to Tn minus 1 and G. It's a subalgebra. But a better, I don't actually think about it as an induced representation. I think about it as it's generated by a single vector, which is this boldface 1, with a relation that if I take Ti and act on boldface 1, I get T to the half I, T to the half boldface 1. And if I act by small g on boldface 1, I get boldface 1. It just has an eigenvector of eigenvalue 1 for g. But now I act by all elements of the Daha on boldface 1 in this way, and that's the only relations I have. Okay, so if I let x to the mu be x1 to the mu1, x2 to the mu2, up to xn to the mu(n). Remember, all of the x's here, they commute. Let's get this screenshot. So all of the x's, they commute. So it acts just like a monomial, x1 to the mu1, x2, and they all commute in a symmetric algebra. All right. And so I'm just labeling monomials. And let's let x small x mu be x to the mu acting on 1. Okay, so then it's not difficult to use the relations of my Daha. I have these in particular, this third presentation. If you believe this third presentation, then it's quite easy from the third presentation to see that this induced representation, this induced module, has a basis which is exactly the x to the mu's for mu in z to the n. All right. So it really looks like it's isomorphic x1 plus minus 1 up to xn plus minus 1. And the Daha is acting on it. So now we really have that y1 up to yn are operators on this representation. And we want to build, so can we construct eigenvectors for them? So they're commuting operators even. So this is our goal. But we have set up our tools so that this is now actually quite easy. Because
Arun, maybe this is a good time to stop and see if people have any questions.
Sure.
I think this is a nice break point. So yeah, we can take a few minutes and just see if anyone has questions. If you have a question, you could just unmute your mic and ask right now.
So is there a relation among the yi's and the xi's?
It's rather complicated. Yes, you can try to write xi, yj, and you get a top term, which is yj xi, somehow as you expect, but then you get some garbage here. And in fact, there's also some factor here, which I think is q to the delta ij or something. So if I ignore the garbage, then in fact it looks like a Vial algebra. So it looks like a Heisenberg or a Vial algebra. But there really is garbage, and you have to learn how to. It's hard to control it, actually. Only in very special cases do I know how to control the garbage.
So is this related to the fact that when you express Mcdonald polynomials in terms of the monomials, you get a top term and some lower order terms?
That's right. That's right.
Thanks.
We could take one more question if there are.
So Arun, you said the yi and the tau I checks. So when you commute the yi past the tau I check, you get tau I check yi plus 1. So that is only for I between 1 and n minus 1. What about the other i's? I mean, you define yi for all integers.
It's
So it's just the q factor just comes out.
The q is a constant. The q is a non-zero complex number. So the q commutes with everything. Yeah. But in this relation, it is true that I think of it only for I in 1 through n minus 1, because the tau i's in my mind are only labeled by, the tau i's correspond to the S1 up to Sn minus 1. So I don't actually need to use it for all integers, even though I probably could.
Okay, thanks.
Okay, so let's move on then, I guess. Yeah.
Okay, well, that was perfect place, because now I can just construct the non-symmetric Macdonald polynomial. Macdonald polynomial. So E mu. This is, so how am I going to build it? Well, I'm simply going to take the element 1, which is my generator, and I'm going to act on it by tau u mu check. So this is where tau u mu is tau I1 check up to tau IL check if u mu is SI1 up to SIL is reduced. So if we remember at the beginning, yeah, I think I didn't make a copy of the picture. This was what we did at the very beginning, was we produced a reduced word for this element. Right. So we produced a reduced word for this element, u mu. This is what we're looking at here. In our example, it came out to u mu was S1 pi, S1 pi, S2, S1 pi. So tau u mu check is going to be tau 1 check, tau pi check, tau 1 check, tau pi check, tau 2 check, tau 1 check, tau pi check. All right, so that's what I mean by tau u mu check. And then there's just the only other thing I need to add here is that there's a small normalizing constant because of the way that I like to write things. And this is 1/2 the length, negative 1/2 the length of v mu. So v mu was my other permutation that transfers mu into increasing order. But the normalizing constant is really very minor. The important part is the sequence of taus, because now we have a theorem. So this is some combination of Macdonald and Cherednik. Which says that these E mu's are simultaneous eigenvectors of y1 up to yn. And in fact, we can write down very explicitly the eigenvalue. If I take yi and I act on E mu, then I get q to the minus mu I. So mu, remember, is a sequence mu1 up to mu n. So mu I is the ith entry of the sequence. And then I get t to the minus v mu of I minus 1 plus 1/2 n minus 1 E mu. So this is the eigenvalue, very, very explicitly. And this is very easy to prove at this stage if you believe the previous things, because if I want to act by yi on E mu, that means that I need to put a yi in front of E mu. And if I put in front of these taus, then I move the yi all the way to the other side of the taus by using this proposition. I move the yi all the way to the other side of the taus. And then I allow the yi to act on 1. And I can use these original relations to act on 1. So this result is really very easy with these intertwiners. So once you have proven this proposition, which is also not difficult, then you can construct this Macdonald polynomial in this way. Okay, so the next statement is that that the coefficient of x to the mu in E mu is 1. And that's because of my normalization. So this was my normalization here. Which guarantees that this coefficient here is 1. In fact, you can write E mu is x to the mu plus lower terms, the way we have written it down. This is what Arun was saying. That so this is the result of how we construct. So I'm going to say one more thing, and then we'll spend the rest of the time doing an example. So
there's a question by Arvind Iyer.
yeah,
He says, well, mu is a composition, not a partition. So, but the E mu, what are they indexed by? Are they indexed by partitions or compositions?
compositions.
Okay.
So these are the non-symmetric Macdonald polynomials. If I had taken, so there are also symmetric Macdonald polynomials, and symmetric Macdonald polynomials are indexed by partitions. But okay, so actually, since you have asked the question, let me just write the relation. Symmetric Macdonald polynomials are P lambda. So lambda now is decreasing. And then you take P lambda, so so-called P lambda, and this is the sum of t to the 1/2 length of z of tz e lambda. Actually, it doesn't matter which. So this is overall z in the symmetric group. And there probably is some constant that I'm forgetting, some normalization, but you can always get the symmetric Macdonald polynomials by symmetrizing. So this is a symmetrizer, a T-symmetrizer. And so you can get the symmetric ones from the non-symmetric ones in this way. Okay.
So there's one more question. Raghavan wants to know, so you've written E mu is x mu plus lower terms. What exactly is meant by lower terms in this?
So let's see if I can say this well okay, so I want to, so I think of it in terms of dominant. So if I take the convex hull, since it's Raghavan who's asked me, if I take the dominance order on partitions, and then and also graded according to the degree of the partition. So the number of the sum of the parts of the sum of the parts of mu is the degree. So I'll order by degree with 0 being at the bottom and everything trying to get closer to 0. And then I take Vial group orbits and go in towards 0. So there is a way to define the ordering specifically and not difficult. But that's the idea, is you take the Vial group orbit and the things inside are smaller, getting closer to 0. Okay, so let me just make one more definition, and that is that the Q-Whittaker function, because this is going to show up in tomorrow's talk, Whittaker function is E mu Q 0. So in other words, it's E mu, which depends on Q and T, specialized at T equal to 0. And so these will arise in the context of, so these are some kind of characters of Vial modules for affine Lie algebras, quantum groups, affine quantum algebras. I should say quantum. Algebras in level 0. And so that's what I will talk about tomorrow, which is it, but just so that we have the notation. Okay, so let's do an example. Let me show you how do I actually build such a Macdonald polynomial. So example. I want to build E012, which is my running example. And we saw that this is because we have so this is, in this case, V mu is the identity, we said. And so we have just tau check U mu applied to 1. That's all we have to do. And tau check U mu is tau 1, tau pi, tau 1, tau pi, tau 2, tau 1, tau pi. Applied to 1. Okay, so you start on the left and you write this tau 1 out. So this is t to the minus a half times t to the half t1 plus 1 minus t divided by 1 minus y1 inverse y2 inverse tau pi check tau 1 tau pi tau 2 tau 1 tau pi applied to 1. So this, all we have done at this point is replace this intertwiner by its definition. Right? Now, this guy here, this is some smaller Macdonald polynomial, E nu. And so we know that when the y's act on it, we get some constants there. And this turns out to be 1 minus qt. Because the smaller Macdonald polynomial is an eigenvector for the y's. And we know what the eigenvalue is. So this qt, which is appearing here, is exactly the eigenvalue of this combination of y's acting on this smaller Macdonald polynomial. So you can compute it directly from the formula I already gave you. And then you have tau pi check, tau 1 check, tau pi check, tau 2 check, tau 1 check, tau pi check 1. Okay, so now I have to multiply this this tau pi check times this t1 and this tau pi check times this 1. This is what I want to do in the next step. And when you do that, let me show you what you get so you can. So remember that this. So let me write it first. So the first one you get is. Actually, in my notes, I have done something good, which is I have written this as a permutation. So I think I have a little bit of a slide here. So these are the relations that we're actually going to use, and these will be helpful. And that is that I can label TW if I have a permutation W, then I can write down TW. And if I multiply TW times TI, I get TWSI. So these T's are going to act like permutations. So if the I comes before the I plus 1, then TWTI will switch it to I plus 1. And if I plus 1 comes first, it switches the 2, except that there's an extra factor of T here. So there are some factors of T, but otherwise I always know how to multiply by TI. So what I really did here is I took T of the identity and I multiplied it by T1 and I got this T213. Right? That's what really happened. Okay, so then the next step is that you get T to the negative half and then x2 T to the half, T132 plus 1 minus T over 1 minus qt, and I have a factor here. I'm going to put some factor t to the minus 2 on 2, just to be careful for a moment, and T312. And then I have remaining all my T1 tau pi check, tau 2 tau 1 tau pi check. Okay, so what I have done in this step is I have multiplied this tau pi. So I have a little lemma here, which I compute for my relations. It says, if I have a TW with a tau pi, then what happens? Well, let's ignore these factors of T. They are a little bit unpleasant. You can eventually figure them out. But what's important is that I get an X here. So in fact, you see that here. This produced for me an x2 here. And that's this x. And then it produces for me another permutation. And this one produced an x1 and another permutation. And how do I get this new permutation? Well, I just take 2 and subtract 1. I take 1 and subtract 1 mod 3. because I'm doing this mod. There's always periodicity in this game. And then I take 3 and subtract 2, mod 3. So this is very, very explicit and combinatorial. Okay, now what we do in combinatorics is we're going to write 2 kinds of tableau to keep track of our computation. The first one is the X tableau. And this term gives me an X2, so I put a 2 in that box. And this term gives me a 1. For the second term, I get an X tableau. And for the T tableau, I also have a T tableau, I put the permutation there. So this is this permutation. This is the T tableau. And here I have 3, 1, 2. T tableau. Okay. So the point is that in each step, we fill 1 box of the tableau. So each step, the computation fills 1 box of the tableau. And we can go recursively and produce the tableau this way. So let me show you the answer, or I have the answer also here after you're completely done, is you get these tableaux, which are called by Haglund, Heyman, Lohr. So these are the Haglund, Heyman, Lohr. Non-attacking fillings. And so I get a formula for the Macdonald polynomial completely in terms of the statistics of these fillings. You can see here that I have 1, 2, and 2 3s. So the tableau really tells me which term corresponds to which. And I have constructed this tableau by recursion from the double affine Hecke algebra action, just using Cherednik-Macdonald definition. And similarly, you can produce even these statistics which come out in front, you can produce them from the tableau. Let me give you a feel for, just a smallest feel for how that happens. If I look here, there is 1 descent, and there is 1 of these parentheses. Whereas here, there is 1 descent and 1 ascent, and there are 2 factors here. So the number of factors, oh, something is wrong with this one. Well, this one is actually incorrect. It should be 1, 2, 3 here. And that's got a descent there and a descent there and an ascent there. And these correspond exactly to these factors, right? So they're really, and the combinatorics is really tight and allows you to construct this polynomial very well. So now we're interested in this Q-Whittaker function. So Q-Whittaker function means set t to 0. This is the condition for the Q-Whittaker function. Well, with this combinatorial formula, I can see very easily which things to remove, because I've got very nice powers of Q and T, and so I can put T equal to 0 and remove the terms as necessary. So most of these fractions, they all collapse to 1. and in fact, that's easy to prove, that every one of these fractions will collapse to 1. And then sometimes there's an extra t out in front, which will kill the whole term, right? Because of this t, it kills the whole term. So some of the terms actually disappear. And when you're done, when you finish killing all the terms, you have 9 terms left in this example. And in fact, one of them still has a coefficient of q in front of it, but the others have disappeared. And it's also quite striking that if you set the q to 0, then this is the Shor function. So this is in the case when, so this is S210. So if this is in the case where if mu is increasing, and lambda is the rearrangement, is the decreasing rearrangement of mu. Then E mu 0 is S lambda, the ordinary Shor function. So we're seeing already the Vial character, which is some hint that in fact maybe this is the character of some representation, some module, which is what we'll do tomorrow. So let me stop there.
Okay, thank you. Let's thank Professor Arun Ram. So we'll take some time for questions. There's already one question on the chat, which I didn't ask earlier. It's from Wei Ying Guo, and he wants to know whether the symmetric Macdonald polynomials are simultaneous eigenvectors of the Macdonald difference operator, and whether there's a relation between the yi and the difference operator.
So I don't know what the difference operator is, but the symmetric Macdonald polynomials, they are eigenvectors of symmetric polynomials in y1 up to yn. So they're not eigenvectors for the individual y1 up to the individual yi, but if I take any symmetric function in the y's, then the symmetric Macdonald polynomial is an eigenvector for that.
Thanks. Yeah, are there any other questions?
Yeah, I have a question. Can you hear me?
Yes, please.
So you introduced a pi right in the beginning, which you joined to the Vial group. Can you hear?
Yes.
And then you use Cherednik-Dunkel theory. Is this a new addition to the theory of Cherednik? The introduction of pi?
No, it was already in Cherednik. So the
Right.
pi is simply so if I consider GLN versus SLN, already, well, if I consider GLN versus PGLN, so for PGLN, the character lattice is smaller, I guess. The root lattice, the co-root lattice is smaller. And for GLN, the co-root lattice is bigger, the co-weight lattice is larger. And this pi is just the addition of the automorphism of the Dinkin diagram that captures that.
Okay, thank you.
So thanks for the nice lecture. I have a question at the last slide. So is there a clear bijection between the case q equals t equals 0, the tableau that you showed, and semi-standard Young tableau?
I haven't. So to be honest, I work with alcove walks more often, and then the analog of semi-standard tableau is the Lakshmi Bai Seshadri paths, and so there it's very clear how the alcove walks specialize to the LS paths. And I'm sure that it's not difficult for this case, but I haven't personally worked it out. So, yeah.
But alternately with GT patterns, is it
Yeah, yeah, you can convert. Yeah, I think it's not difficult. Maybe Evgeny, I saw him here. Do you know?
Pardon me. So could you please repeat?
Do you know how to take the t equals 0 non-attacking fillings and make a bijection to semi-standard tableau or Gelfand-Settler patterns?
Well, I'm not sure about the concrete bijection, but so there are some way to identify, but I don't know the exact simple formula.
Ah, okay, but it's probably known.
Yeah, I think it is known, but I just can't formulate it in some few minutes.
Yeah, it's certainly not difficult because on the level of Littleman paths, it's very direct. So,
Thank you.
Actually, may I ask a question?
Yeah.
So you explained the t equals 0 specialization for increasing compositions, but do you know any sort of such statement for non-increasing compositions?
What kind of statement are you looking for non-increasing?
So if you're taking non-increasing thing and then specialize at t equals 0, you are getting something. So there's some expression involving q. So is there some representation theoretic incarnation, some representation theoretic construction describing that?
Yeah, yes, but I feel like I learned this from you. This is a de Mazur module in level 1. So if I take or a de Mazur module in level 0, but just not for an extremal weight which is dominant or anti-dominant.
Yeah, but but the problem is, so I mean, how to put it?
So the de Mazur module, if I think about it, at the bottom it has some initial starting state, and then it kind of fills out to this Whittaker function.
Yeah.
And so the little finite piece at the bottom is sort of degree 0 of the Heisenberg action. That's this this character.
Yeah, I see. Probably I was wondering about some concrete combinatorial, but right. So I see. You're right.
But we can also write a combinatorial version, so I can describe exactly the paths which live in that piece. Yeah, but I think it's not different from what you did. Yeah.
Probably right. Probably you're right. Yeah. Thank you.
Okay. Are there any more questions? Well, if there are no more questions, maybe let's thank Professor Arun Ram again, and can unmute your mic. So we have 5 minutes before the next talk begins. So you can, grab a glass of water. 5 for Professor Arakawa's first talk.